Let sigma be some finite alphabet. We've defined a regular set over sigma to be any set that's accepted by some DFA over sigma. An alternative path to the same concept makes no mention of DFAs, but rather arises naturally from our operations on sets of strings. In this video, we'll present this second formulation of what it means for a set to be regular, and later on, we'll see just why these two formulations of regularity are logically equivalent. So for now, forget everything you know about DFAs, temporarily, and we'll take a fresh look at regular sets from a very different perspective. We've introduced several operations that we can use to build sets of strings over sigma, in other words, subsets of sigma star. Sums, products, powers, and asterisks. We use these operations to define a regular set over sigma as any set of strings that can be built from any finite sets of strings, in other words, any finite subsets of sigma star, including the empty set, combined in any way via our operations of sum, product, which includes powers, and asterisk. When we combine these operations in a more complicated expression, keep in mind our usual order of operation: asterisks and powers, then products, then sums, just as in regular algebra. Let's make a few initial observations about this new concept. First of all, any finite set of strings is regular, because we don't need to use any operations at all, just take that finite set. These finite sets are our initial building blocks for all other regular sets. Thinking about our permitted operations, if we took the sum, or the product of two finite sets of strings, we'd again get a finite set of strings. So these don't get us any new regular sets, at least not yet. The asterisk is a different story. The asterisk of any set of strings with at least one non-empty string in it will be infinite, because at the very least it will have all powers of that one string. So asterisks of finite sets give us our first examples of infinite regular sets. The set A star is an infinite regular set, consisting of the empty string, A, AA, AAA, and so on. So is the entire set sigma star, remembering that sigma is a finite set. And so is the set AB star, which consists of the empty string, AB, ABAB, ABABAB, etc. Note that asterisking a set of strings twice just gives us its asterisk. All products of strings from a set W are products of strings in W. In other words, W star star is the same as W star. Thus, we never need to apply two asterisks in immediate succession. Our definition also tells us that if two sets A and B are both regular, then their sum, that is union, A plus B, is also regular. Just build A and B from finite subsets of sigma star and add the results. For example, A star plus B star is a regular set. This is a set of all strings containing just A's or just B's. So is their product AB, consisting of all concatenations of a string in A and a string in B. Again, just build A and B from finite subsets of sigma star and multiply the resulting sets. For example, A star B star is the regular set of all strings consisting of a non-negative number of A's followed by some non-negative number of B's, which you could also write as A to the m, B to the n, where m and n are greater than or equal to 0. This set might ring a bell from our work with DFAs. Finally, the asterisk A star of a regular set is regular. Just build A from finite subsets of sigma star and asterisk the result. For example, A star plus AB star is a regular set. It gives us all strings in which every B is preceded by an A. Thus, more and more intricate regular sets can be created from other regular sets via the operations of sum, product, and asterisk. Taking our last example, this regular set contains every string that can be built using strings of just A's and strings built from AB's. It seems like this would be exactly the same as just AB star, the set of strings that can be built from A's and AB's. Perhaps there's a list of rules for these constructions of regular sets that tells us when two expressions give the same set. There is, and by the end of this video, we'll see those rules. Okay, time to recover what you know so far about DFAs. We've now provided two definitions of a regular set over sigma. Sets that are the language accepted by some DFA over sigma, or alternatively, sets that can be built from finite subsets of sigma star via the operations of sum, product, and asterisk. These seem a bit disparate, both in terms of their definitions and their observable properties. One of our tasks moving forward will be to prove that they are in fact logically equivalent. you might compare and contrast what we said about regular sets in terms of these two perspectives, and we'll do so in the next video. But before we leave this new perspective on regular sets, we have one more thing to discuss: regular expressions. The way we build regular sets, combining finite subsets of sigma star via the operations of sum, product, and asterisk, can look very complicated, with all these sets, braces, plus signs, asterisks, and parentheses. Most of this is unavoidable, but we can unambiguously get rid of all the braces if we do the following. Write each non-empty finite set as a sum of singletons, using parentheses as necessary. Then drop all braces around singletons. For example, we can write the singleton A star simply as A star. 101, the set 01 star 00, becomes 101, 0 plus 1 starred, 00, and so on. The result is called a regular expression, which looks a bit simpler but does hide a bit of the true nature of what's going on. All of this really concerns sets of strings, but we've hidden all of the braces. Keeping in mind the usual order of operations, asterisks and powers, then products, and then sums, we can read a regular expression as presenting a pattern for a given string to match or not. Each part of the regular expression really represents the set of all possible matches to that part. In this last regular expression, the 101 literally matches the string 101. The asterisk matches any string of zeros and ones, and the last bit matches the string 00. Altogether, the regular expression represents the set of all strings matching it. The string 1001100 would match the first two characters but not the third, and thus would be rejected by this regular expression as a non-match. On the other hand, the string 10100111100 would be accepted by this regular expression as a match. The first three characters match the 101 in the regular expression. The next five would match the asterisk, any strings of zeros and ones would match the asterisk, and the last two match the 00 in the regular expression. In this way, every regular expression alpha yields some set called its language L of alpha of all strings matching the pattern given by alpha. It's important to note that L of alpha is just the regular set we get if we correctly read what the regular expression means as a combination of finite subsets of sigma, and this is a correct way to understand them. A regular expression is just a convenient way of expressing a regular set. While a regular expression looks simpler, don't forget that it really is giving us a set of strings. With regular expressions in hand, each of which generates a language of strings, a natural question would be whether we have any rules for manipulating regular expressions. In fact, the answer to this question is a resounding yes. We'll call two regular expressions equivalent if they generate the same language of strings. In a diagram, alpha and beta are equivalent just when the languages they generate are equal. Then the Kleene axioms can be used to turn any regular expression into any equivalent regular expression, that is, any regular expression generating the same language of strings. The axioms are as follows, using a bold 0 for the empty set and a bold 1 for epsilon, which really means the singleton epsilon. To start off, alpha plus beta plus gamma is equivalent to alpha plus beta plus gamma, and alpha plus beta is equivalent to beta plus alpha. Second, alpha plus alpha is equivalent to alpha. The union of a set in itself is itself. And alpha plus 0 is also alpha, because this is simply the union with the empty set. Products are associative. Alpha beta gamma is equivalent to alpha beta gamma. The empty string is the identity for products, which is why we write it with a bold 1. 1 times alpha is equivalent to alpha, which is equivalent to alpha times 1. As we mentioned before, products distribute over sums. Alpha beta plus gamma is equivalent to alpha beta plus alpha gamma, and alpha plus beta gamma is equivalent to alpha gamma plus beta gamma. The empty set is a multiplicative annihilator. Multiplying a regular expression by 0 on either side is equivalent to the regular expression 0. The empty string has an interesting property with asterisks. 1 plus alpha star alpha and 1 plus alpha alpha star both are the same as alpha star. In other words, to match alpha star, you must either be empty or match a product of alpha and alpha star in one order or the other, using at least one alpha to be built. We have two more rules to complete the axioms. They're used for deducing additional equivalences. Writing alpha less than or equal to beta to mean the language of alpha is a subset of the language of beta, we have that if alpha gamma is less than or equal to gamma, then alpha star gamma is less than or equal to gamma. In other words, if gamma matches every string of the form alpha gamma, meaning adding any string matching alpha in front of it still matches gamma, then we can add as many of those strings matching alpha as we like. The same in the other order. If gamma alpha is less than or equal to gamma, then gamma alpha star is less than or equal to gamma. The abstract object defined by these axioms is called a Kleene algebra. Regular expressions are a prime example. We won't go deeply into these axioms or Kleene algebras, so you don't need to worry about learning them, but Kozen discusses them in Appendix A if you're curious. In this video, we've provided a second definition of regular set, one that can be built from finite subsets of sigma using sums, products, and asterisks. We'll later prove that this is logically equivalent to our definition of regular sets as language accepted by DFAs. Regular expressions are a slightly simplified notation for regular sets, and they can be interpreted as a means of presenting a pattern to match. Any two regular expressions yielding the same regular set can be changed into one another via the Kleene axioms. The abstraction of a Kleene algebra puts all this into a formal framework which we won't explore in any depth, but this is the key to proving a significant result about DFAs that we'll note later on.